Hello everybody, JT's Physics of Cycling video number 6, I believe. Excuse me while I clean up. But I know all this seems academic, maybe too academic, too mathematical, but I do plan on bringing this back into some models that you as non-physicists, and I'm not even a physicist, I minored in physics. I have a degree in geophysics, but you know, I'm not the world's greatest physicist by any means, but I do plan on bringing this back once I describe all these rules and laws of physics, back into something that you're going to be able to use as a cyclist to understand the forces that are acting against you when you're out there trying to achieve your best. This is Sears, Szymanski, and Young, University Physics, 7th edition. This is actually 3 semesters of sophomore level physics. I had this class at Western Kentucky. This book is outdated, so I'm going to use this book to demonstrate the differences between force, energy, and power. Now, force, energy, and power are all 3 derivatives of the same thing, namely motion. But the first thing that we need to talk about is force. Right now, there's a force acting on this book, on University Physics, and the force is static. It's a static force. In other words, there is no motion. But just because there's no motion doesn't mean there's not a force being applied to the book. In fact, gravity is pressing the book down on the table. The table is pushing back on the book, and the forces cancel themselves out. Now, I want to go ahead and talk about gravity. So, one more point on force. Force can be thought of as weight. Especially in a gravitational field. Okay, so let's suppose that I lift this book, okay? In other words, I do work on this book, and I'm going to lift it through the gravitational field. Work and energy are the same thing. So I'm going to apply a force and do work to this book and give it a higher state of energy. I've done work on this book. I have applied a force to the book, which overcame gravity, and I applied that force over a distance, and that's the definition of energy. Force applied through a distance. It's also the definition of work. But what have I done? I have given this book what's we call in physics potential energy. In other words, I've raised its energy state relative to its beginning point, namely the surface of the table. And it has a higher energy state. I'm currently applying a force to the book to keep it stationary in Earth's gravitational field. So the book wants to go down through gravity, but I'm holding it up, so the forces are equal and opposite, and so that's a static situation. And it has a potential energy equal to the height above a given reference point times its mass times the acceleration due to gravity. But what happens when I let go of the book? The potential energy is converted back into kinetic energy, and those 2 quantities are conserved. So the work that I've done to the book to get it to this state is going to result in a certain velocity when it impacts the table, and the energy is going to be conserved. So the higher I lift the book, the faster it's going to go when it hits the table. I was hoping that the table would handle that. Okay, so that's energy. But I want to go back to force just for a second. There's other forces. Let's say that I apply a force to the book this way, okay? And I apply a force and I do work to the book in that manner as well. So we don't want to just use gravity as the reference. Now, what is power? We've talked about force. We've talked about energy, force being weight. Energy is the amount of force applied through a certain distance, But what's power? Power is the application of, or the addition of energy to an object divided by the amount of time it took for you to apply that energy. So if I were to lift this book from, say, the surface of the table to 3 feet above the table, and this is a massive book, I mean it's 3 semesters of physics, university physics, in 1 second, then I have used a certain amount of power to do that. Now let's suppose that, and that was energy per unit time. Now let's say I do it in half a second. So if I can raise this book in half a second. That's about right. So I applied twice as much power because I did the same amount of energy, but I did it in half the time. Okay? And it goes on and on and on from there. Power is the consumption of energy per unit time. So if I raise it really fast, then you know, more and more power. So consider as a cyclist, you have to apply a force to your pedals to climb a hill, and if you're applying a force through a distance, which you are when you climb a hill, then you're doing work. And the amount of work that you expend, or the amount of energy that you expend, work and energy being interchangeable, you're going to be able to get back out minus the forces of friction that you're going to encounter coming back down the hill, and we've had videos on that already. We're going to introduce friction as it's meaningful to a cyclist in the next video. But power. Let's say that I climb a 3/4 mile hill that has a total vertical relief of 300 feet in 5 minutes, and someone else does it in 2 minutes. Well, they have output a whole lot more power than I have by climbing expending a certain amount of energy, the same amount of energy, in a much less time. And units of energy, or power, could be in horsepower in the English system, or watts in the metric system. By the way, units of force are newtons in the metric system, and foot-pounds in the English system. Energy is joules in the metric system, and I'm sorry, pounds would be a unit of force in the English. Foot-pounds would be a unit in the English. And so I think that explains the difference between force, energy, and power. And in the next video, we're going to start talking about the forces and the amount of energy and the amount of power that works against us as we move through air as cyclists. Okay, I hope you bear with me. I'm going to bring this back to something that's very useful to you here in just the next few video episodes. Thank you all very much. Good night.